the slides for today, and I copied the slides from lecture 5, which was from Wednesday, to the start of the lecture 6, and then simplified them. So don't worry about the ones that we didn't get to last day. We're starting with the slides in lecture 6 uploaded file today. Okay, so they contain essentially the same information, just in a more concise manner. Does anyone have any questions they want to ask before we get into the lecture material today? Assignment number 2 should be out. Anybody? Everybody just hanging in there? Same. I get it. Okay, well, let's then get into this. Oops. So we're using the file, the uploaded file for lecture 6 with today's date. Okay. All right, so you guys, you took circuits class in term 1. So you have some experience with currents and circuits, charged particles moving, resistors, I think, but I think today is the first time we're going to be talking about conductors and capacitors, I think, according to the course outline. Okay. So let's get into it. So if you remember from day 1, and you may not because we're going at light speed here, conductors are materials where some of the electrons are free to move around. Not every electron, but some of the electrons, you know, that are loosely bound to the nuclei of the atoms and molecules in the material. They are able to move around in the material, carry charge from place to place. And conductors make it relatively easy for them to do that. And insulators are materials where the electrons are fixed or bound to the material and not free to move around. I hear someone's mic on. I think it's Dawson, maybe. You might want to mute your mic. I think. Okay. All right. So what we're going to talk about is, you know, how those charges, those charged particles that can move, the electrons, what they do when they're in a conductor. So a conductor is commonly a metal. Copper is a really common, really good conductor, and it's used in, you know, electrical wiring in your house, in circuits, and so on. So it's a really good conductor. Electrons are free to move. So what happens if you have a conductor with some excess charge on it, kind of distributed throughout the conductor? This top picture is trying to represent, you know, some initial state where you've got charges in a sphere, a conducting sphere, that are free to move. Well, we've got some minuses, 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 minuses all through here. They repel each other, right? Like charges repel each other, and because they are able to move in a conductor, they feel forces that push them as far away from each other as possible. Okay, so if you have a conductor that, you know, you give it some charge, the charges will immediately spread out to the surface because they repel each other and try to get as far away from each other as possible. So that's the simple concept. We can talk more about, you know, specific things like equilibrium and what the electric field looks like and things like that. But essentially, if you put a charge on a conductor, they will repel each other, and because they're free to move in a conductor, they'll spread out to the surface. Okay. Look good. And they basically get to the surface and they'll move until all of the forces eventually balance out, and then everything becomes still and it's at equilibrium. So eventually it will come to a balance where the charges are sitting on the surface. Okay, so charges will spread out to the surface and then, you know, sort of adjust themselves until all the forces balance out, and then they're at rest, and that's kind of its lowest energy state. Okay, so we'll go through these properties one by one. The excess charge on a conductor, so we have extra charge here, sits on the surface, like right at the edge, and that's because of that repulsive force between the like charges. Okay, so if any extra charge was placed inside, it would immediately be, you know, feeling that repulsive force and be pushed to the edge. Okay, so that's one thing we need to know. The electric field at the edge is always at right angles, perpendicular to the surface, because we know that if there's any force in a direction that one of those electrons at the surface can move, it will move. So if there's any force, you know, any force that's not perpendicular has a component parallel to the surface, and that produces a charge parallel to the surface on one of these little charges that's sitting on the edge. Okay, in this case, we've drawn it as a positive. That's fine, doesn't matter. So what happens then is you have movement here, and it probably, like, you know, bumps it into a nearby positive charge, which will repel it and create a, you know, electric force pushing back in the opposite direction. So the presence of nearby charges mean, and the ability to move mean that they will sort of battle it out and find a place where they're happy to just sit. So at that point, the force along a direction inside the object is zero. Okay, and the only portion of the electric field that's left is perpendicular to the surface, and it exists, right? It sits there, but it doesn't do anything because it can't leave the surface. It's bound to the material. So at this point, you've got an equilibrium condition where, you know, the tension forces or whatever, the chemical bonds of the material are holding the charge inside. The electric force is pushing it away, but it can't escape the material, so it just stuck there. It just sits there. Okay, so the charges move to the surface and they shuffle themselves around until all the electric force and the electric field is in the perpendicular direction to the surface.
So while they're moving around, that's when they have that kind of angled force.
Yeah, exactly, exactly. You need this, like, component of the force to move around. But if we're talking about, you know, charges being distributed all around the surface, if it moves closer to a positive charge, it will feel a repulsive force from it, so it will push back against that force. So those just sort of, you know, battle it out until they cancel each other out, and then they find a place where they can sit, and the force to the right and the force to the left is the same. So that means there's no electric field in that horizontal direction in this picture. Does that make sense?
Yeah.
Yeah, and this happens like almost instantaneously. So it's not like we got to wait 10 minutes for these things to do this. Like, it's very, very quick. Because these things have a lot of ability to move in conductors, and they can, you know, they can sort this out extremely quickly. Okay, and then this, hopefully, I hope, oh, maybe instead of telling you why, I'll ask you, does anyone know why the electric field might have to be zero inside this charge conductor? Anybody know what formula we might be able to use to show this? That you used in assignment 1, question 7. Anybody? How would we maybe prove that the electric field is zero inside?
You'd use 2 KEQ times the lambda divided by R, I think.
Yeah, that's for the cylinder. So if you had a cylinder, that's the one you'd use, right? What's the more general version of that? So that's right. What's the more general version of that?
The charge will be zero inside.
The charge enclosed is zero. So remember, I draw it with 2 lines. The textbook draws it with 1. But remember Gauss's law? Okay, so if we make our little Gaussian surface in here, right? There's no charge enclosed. So everywhere you put a Gaussian surface right up to the edge, There's no enclosed charge because it's been pushed all to the surface, right? So because of Gauss's law, we can show that the electric field has to be 0 inside the conductor. We also know it has to be 0 because we don't have any force in there. Like the electric field is related to the electric force, and no charges are moving around inside. They've been pushed to the edge. Everything is like been evacuated from the center of the object right to the surface. So there's no charges moving around inside. So that means you can't have any forces acting in there. So we've got two kind of ways to think about it. Gauss's law tells us there's no charge enclosed inside a conductor. And there's no moving charges in there. There's no forces there. Okay, so those two things together hopefully help you remember that.
Is that supposed to be property 3?
Oh yeah, yes, that's supposed to be property 3. Sorry, I
Okay.
changed these around. You'll see if you look at the slides from last day, they were in a different order. Yes, it's property 3.
Okay, thank you.
Thank you. I appreciate the edit. I really do. What was the next thing I was going to say? Oh, there's an implication here for Gauss's law questions. It means that if you get a charge, if you're told in a question that you have a charged or a conductor with some charge, do you think you treat, like if you're solving Gauss's law, do you think you treat it as a solid object with a uniform charge or a charged sphere or a charged surface area? What do you think? Anyone?
Would it
How
be a
about
charged
hold
surface
hands up
area?
if you think it's a solid thing with uniform charge? Don't see hands up. Surface, charged surface. Excellent. I see hands up. This is so good. This is so good. So if you are given a question where you're told you have a conductor that holds charge or a charged conductor, you treat it as a charged surface because all the charge has moved to the surface. So it is effectively, it's effectively like a sigma surface charge question now, instead of, even though the object is 3-dimensional, only the surface has the excess charge on it. Really good, everybody. So when you're doing an electric field question or a potential question, that is one place, like make a note of this to yourself, that that's sometimes where people go wrong when they're solving these questions. They assume that the charge is distributed throughout the object, but that's not true for conductors. If the charge is distributed uniformly throughout the object, we will tell you. But if we say it's a conductor, you know that all the charge gets, pushed right out to the edge. Excuse me. Another weird thing, another thing about conductors is that the charge tends to build up on the sort of sharper curves. So the tighter the curvature, the more charge accumulates there. And I'll show you why in a second. But you'll see here that at point A, quite a bit of plus signs representing like a lot of charge buildup here. Whereas on this big kind of not so curvy part, we have fewer charges per, the same length. So charges build up on the surface. And to prove this, maybe like, let me know if you have any questions as we go through this, because it's kind of a weird way to think about it, perhaps. Perhaps it makes sense right away to you, but if we have a small sphere, okay, with some, this is sphere 2 with surface charge density sigma 2, it's a conductor. So all the charge is moved out to the surface. So we talk about a surface charge, right? We have, so this is sphere 1 and this is sphere 2. Even small, it's too small for me to read. Okay, and this is sphere 1. Okay, and this has sigma 2 and sigma 1. It has radius 2 and radius 1, and they're connected by like a wire or conductor. Okay. So what that wire does, this connection, it holds the potential constant. So the potential of this surface charge and this surface charge are the same because they're connected by this conductor. Okay. Is that stressful for anyone? Is anyone wondering why that's happening? Basically, this wire is another path by which charges can move back and forth until everything settles out to equilibrium. And when there's no electric field, there's no potential difference. Okay. So that electrical connection keeps the two objects and the wire at the same potential. Okay. When E is 0, when there's no force moving charges around, then the potential is constant. Anyway, so if the potential is constant for each object, we know that like just outside the surface here, the potential, this is equal to K, 1/4π is equal to K. So the potential of a sphere is KQ over R in general. Okay, that's the general formula, KE, I guess, over R. So just outside this sphere, right where the wire connects to it, it's this one here. I've got my twos and ones backwards. We've got KEQ2 over R2. Because it's connected electrically to sphere 1, then sphere 1 is KEQ1 over R1. It equals KEQ2 over R2. So the voltages, because they're electrically connected by that wire, the voltages are the same right where this wire connects to each surface. Okay. So we're putting the radius of the spheres in here. So we're considering like just like infinitesimally far outside the sphere, this is the potential here. Okay. And if we make them equal to each other and cancel out terms, substitute in the surface charge density, we get this equation at the bottom here. So we've got kind of a proportionality. The surface density of sphere 1 times its radius is equal to the surface density of sphere 2 times its radius. Okay. So the left-hand side is equal to the right-hand side. Okay. The right-hand radius, or this R2, which is the small sphere, R2 is small, so sigma 2 must be bigger than sigma 1. Okay, I'll go here. If we rearrange this, the radius of these circles, oops, this is the effective, radius of this circle here, RD, and RC is very small. If we rearrange that formula that we just derived, the ratio of the radii tells us how sigma, like the surface densities at these regions where the curvature is being determined, are related to each other. Okay, so RD is greater than RC, so this number is greater than 1. RD over RC is greater than 1, so sigma C here must be greater than sigma D. Okay, so this tells us that the tighter the curvature of the surface, the more charge sits there per unit surface area. Does that make sense? Anybody got any questions there?
So in a question, we just be told that they're connected by a wire, and that's the only time that this would apply?
You don't necessarily need to connect objects by a wire. This is just a way to prove this using a potential, like for the sphere that we know. In this case, the surface isn't connected by a wire. It's actually part of the same surface. So the whole outside of this thing is going to have the same value of potential. There's no potential difference along this surface, because if it were, charges would be, moving around. Okay, so basically you just need to know the concept that the charge is concentrated in regions where the curvature is tighter. One application of this is lightning rods. You might think of them as a cylinder, but essentially they're kind of conical shaped, and they create a really, like, any excess charge sits on this really tightly curved top portion here. So we've got a strong electric field here. So any, breakdown of the air with the lightning, so basically producing free charges in the air, they feel this force here and are attracted to the end of the lightning rod rather than being attracted to nearby objects. It makes the lightning rods a really attractive target to free charges in the air in lightning. Okay. Also, lightning rods can, like, basically any excess charge in the building sits here. When you have a lightning storm, there's often a nice electric field between the ground and the clouds. So you can, produce a little bit of a potential difference or electric field to the top of your lightning rod from your house. All right, so that's mostly conceptual. So conductor, any excess charge in a conductor goes to the surface, and they shuffle each other around until they're in equilibrium. At that point, the electric field is perpendicular to the surface, and the electric field inside is 0, okay? And when you have a shape that isn't the same curvature everywhere, the charge density at the pointiest parts, I guess, is highest. Okay, so these top 3 are the ones you're going to have to be mostly thinking about. The 4th point is for your information mostly. You need to know the concept. So you might have a multiple choice question on it or something. But the top 3 are the ones you'll have to do questions about. Okay, so we'll do one. Or we'll go through one. Okay, so if we have a charged conductor, so a sphere of radius r, and it has some excess charge on it, we know that all the charge has to go to the surface, so it looks like a spherical shell of charge. We know that the electric field inside has to be 0. So here's our charge up here at the top. I think my mouse still freezes probably, but anyway, so we've got our sphere at the top. Look down to this panel down here, the bottom panel of the graph. We know what the electric field of a charged sphere is. We can do this using Gauss's law, but we've also seen it before. So the electric field of a spherical charge is Ke times Q enclosed. So that's the total charge on this sphere divided by r squared. So r is the distance from the surface of the sphere. Okay. So the electric field falls off like 1 over r squared. And you get to the surface right where the charge is, and the electric field has to drop to 0. So the graph of the electric field has 0 inside the sphere, and then it jumps up to this thing that looks like the electric field from a point charge. Does that make sense? Anyone got any questions about that?
Wait, sorry. The big R is kind of the radius from the center of the sphere to the outside of the sphere, and then the small r is from the outer shell onward.
Yeah, r is like any distance out, like to some point P, whether it be outside or inside. So your radius r is the distance from the center of the sphere, and it's any number.
And
Good
the
question.
big R is just to the shell, though?
Just big R is the radius of the,
Okay.
the conducting sphere. Yeah.
Yeah.
Okay. So R is a constant in this case. Capital R is a constant in this case. And little r represents the distance from the center. So from little r equals 0 to capital R, the electric field is 0. And then for little r greater than capital R, it looks like a point charge, this spherical conductor. Okay. Anybody else? So this is really important concept, and this could be on your module test. So make sure you ask questions if this is looking weird. Okay. Okay. Now we want to relate this to potential. Last day we talked about the potential due to a point charge, and we we set the potential equal to 0 and infinity, and then we integrated. Delta V is minus E dot D. What's our unit length? S, I think. Oh, you know what? All right, I'm going back here. I got the wrong, this should be A in your formula sheet. Gauss' law is E dot dA. In our textbook reviews last year, S was the surface, the surface area variable, so I apologize. So Gauss' law is E dot dA, just feel excellent. And then here, E dot ds, which is the line integral. This is this kind of work calculation, energy calculation, the force in the direction of the motion. So we came in from infinity, and we saw that the potential increased, towards the charged object, and it was kq over r. That was our potential. E dot ds. This was the formula we derived last time. So we get to the surface of the sphere, and all of a sudden, E is 0 inside the sphere. So when we do E dot ds, if E is 0, then the potential is not changing. So this becomes a constant at whatever value it reached by the edge of the sphere at radius capital R. Okay. So the electric field is 0, which means we're not changing the potential of difference of if a charge is, or if we're moving in from infinity to the surface, we see the potential increase. We get inside the sphere, and then the potential is just the same everywhere, the same voltage everywhere inside the sphere, because there's no electric field. There's no way you can change the potential energy of a charge in there, because there's no forces acting on it. The electric field is 0, okay? So we've got electric field coming in, and then dropping to 0, and then the potential coming in and being constant, okay? The temptation is to make the potential drop down to 0 as well, but that's not what happens. It just stays at the same value as it is at the surface. So the voltage or the potential of a conductor is the same everywhere. That's why that's why this thing, we don't need the wire to connect things together. The potential is the same everywhere in here. That's how we set them equal to the same. This was just a tool to help you think about two separate spheres, okay?
So the potential on the surface of a conductor is equal to the potential inside a conductor then?
Correct.
Okay.
It's all the same. So if you think about like a ground plate from like your home electrical system, you put a ground plate out, you bury it in the yard. The whole thing, the big sheet of copper or whatever it is, everything is at ground, including the inside, like it's all grounded. So as soon as, if you were to, if lightning hit your house and you were to discharge some, or you had a power surge or something in your house and you discharge some power to the ground, immediately the voltage, like the charge is distributed to the ground, the earth, and that plate stays at the same constant potential, okay? So all of this, like the voltage being the same everywhere and the electric field being 0 is part of this, like get the charge out to the edge. The ground plate can move it even further away, but basically the conductor is at the same voltage or the same potential everywhere. If your sphere was a bit bigger, then you would only, you'd only get, this much potential increase from infinity, and your voltage would be constant at a lower value everywhere if you had the same amount of charge on a bigger sphere, right? And then here your electric field would drop off, a bit sooner. You have the same amount of charge. Your hand up?
I'm just curious, like, does that mean that if you shock yourself, the charge immediately, like, distributes itself evenly throughout your body?
Yeah. If you are doing something like out in like imagine you plug something in you plug something in and you get an electrical shock from the, the plug of the thing, from the socket, the wall socket or whatever. The charge will basically move through your body into the ground. It's just trying as fast, it's trying to get as far apart as it can. Your body is like that wire between those two spheres. It provides a path so that the charge can go into the earth and then be really far apart. So it's sort of like that. If you were insulated, it would definitely distribute all over your body. But if you were touching the ground, it would pass through you and then go into the ground and separate out as far as it could. If you had really good like rubber-soled shoes, then it would be distributed on the surface of your body.
Okay, thank you.
Yeah. Have any of you ever seen the what's it called? Oh my goodness. That, the big sphere. I just can't remember the name of it. The big sphere.
Vanderbilt? Is it a Vanderbilt?
Van der Graaf.
Van der
You put your
Graaf.
hand on it and your hair like stands up like this, right? So there's some charge on this big metal sphere, conducting sphere, and you stand on an insulator. So it's like a plexiglass plate or rubber or something. So your body gets that charge and your hair stands up perpendicular to the surface of your head, just like it, because the electric force is like pushing the charges along the electric field coming perpendicularly out of your head, because all the charge is sitting on the surface there. Okay. So Van der Graaf. If you Google it, you'll see some videos of it. We have it in the physics department. It's very cool. Although I don't like using it because it's quite high voltage. It's kind of dangerous, but anyway. You have to approach it with your key. So so you don't shock yourself really bad. You gotta let the charge go through the key and kind of spread through your hand. You need that contact. Anyway, that's an aside. Okay, so we'll move along with that. Like after that, capacitors, unlike conductors, capacitors can hold charge. Okay, conductors move them around, and sometimes they get stuck. But capacitors are good at holding charge until we hook it up to a conductor when we need it. Okay, and dielectrics are something that help us do that, but we'll get to that in a minute. So, if we have a battery which has had some like chemical work done for the case of an acid battery, there is some potential energy in there that when the chemical reactions happen, it converts the chemical energy into electrical energy. Anyway, basically what it means is we've got a battery where we have a high potential side and a low potential side. And electrical charges have basically been separated in the battery and they're held there. Okay. We do that through like rechargeable batteries. You basically push the charges apart and hold them. Chemical batteries, acid batteries, you need to separate the charges using chemical energy. So a battery holds charges. You hook it up to a circuit, and when you do that, the positive plate repels electrons, and the negative plate attracts electrons. So you've seen resistors hooked up to batteries. And the reason that you can have a circuit flow through a resistor is because you've got some potential difference between the positive and negative terminal, which means you have a voltage difference, which means you can produce an electric field out of these terminals, or an electric force out of these terminals, okay? So the high voltage or positive side pushes electrons out, the low voltage or negative side pulls the electrons in, and that basically creates a current. If we put two big metal plates in here, then we can push some negative charges out. Did I get that right? No, I got that backwards. I apologize. The positive charge attracts the electrons towards the positive high voltage side, and then the negative terminal repels the negative charges out of the negative terminal. So this is the low voltage. Sorry, what day is it? Okay, this is the high voltage or the plus side. This is the low voltage or the minus side of your battery. Okay. We did this with our parallel plate capacitors. Remember, we had minus, and this was low voltage. This was high voltage. And the electric field went from high to low. So same here. We've got the high voltage positive side, the low voltage negative side. So the positive terminal attracts the negative charges, like we remember with the parallel plate capacitor, which draws negative charge away from this plate, leaving it with a net positive charge. And the negative charges are repelled by the negative or low voltage side of our battery, pushing negative charges to the negative plate. Okay? So the charges flow until there's some equilibrium. Like these plates can hold some charges. So they flow until they no more can flow. They hold the maximum charge here. As charges build up, you start to get an electric field produced between these plates that starts to work against the electric field or the voltage in your battery. So charges flow until the electric field between these plates grows big enough, and you'll have a delta V across these plates. Okay, so the charges flow until the delta V across the plates is equal to the delta V across the battery, and then everything stops moving because there's no more force that can happen. Okay, there's a balance there. Does that make sense? After that slight wrong detour, my apologies. Okay. Okay. So if we hook a capacitor up to a battery, we can charge it up. That's what we call it. We charge a capacitor. We put charge on the plates from the battery. Okay. The first experiments with this, with holding charge, was done with a thing called a Leyden jar, and it was a glass bottle with a electrically conducting surface, I guess. And so the difference between the tin on the inside and the tin on the outside and the glass in between allowed some charge to be held in there. I didn't know why at the time, but I won't show it today because it's kind of long, but I recommend if you like history and the history of science, this is a really good video. It talks about how the earliest experiments with capacitors, with these Leyden jars, nobody knew what was going on, but it became a big, huge show. So they would gather people together, and then they would just electrocute themselves to show them how they could get all this electrical charge. And there's one part where this lady talks about they lined up a whole bunch of monks, I think, holding hands, and then they shocked them all, and they all immediately felt the charge go through their bodies and stuff. Anyway, things happened then before health and safety was maybe a higher consideration. But anyway, this is a nice video if you're interested in the history of science. So this Leyden jar, they were able to use friction, static electricity. Remember we talked about how you could rub two objects together like a balloon in your hair or the glass rod and the silk cloth, and you could separate charges that way. They were able to separate charges and hold them in these jars, which seems quite literally holding charge. But this Wimshurst machine is a way that you can do that. There's little brushes on these metal rods here, and you crank this machine and this wheel turns around, and there's little bits of metal on the surface of the wheel, and that brushing creates a static, electricity force that separates charges. And I'll show you this. There's a really nice MIT demo on this. Oh, we got the ad here, hang on. Never mind about the Grammarly. Oh, I'm frozen now, if you're wondering if it's you. Let me know if you can't see this. I probably forgot to set up the sound here, so you probably can't see it, but nobody's talking or anything. Everything is demonstrated or told to you through the words. There's a lot here that they go through. It's kind of confusing, I think, but basically what they're saying here is that the wheels are spinning, and those brushes that are brushing past, like the wheel is brushing past the brushes or spinning past the brushes. Those brushes pick up the charge that's generated through the static electricity frictional method. Okay, and then they eventually move like positive charges to one jar and negative charges to another jar. The video keeps stopping, so if you think it's freezing, it may be freezing, but it may just be the video. So you can see this thing is spinning and they're basically moving charges. Negatives go to the left-hand jar, positives go to the right-hand jar in this case. Some from the front spinning plate and some from the back spinning plate. Okay.
Do they go to a specific side because of the way it's spinning, or is it just because one picks one side first and then the opposite doesn't want to go there?
I'm not sure specifically what the direction has to do with it, to be honest. But the machine is set up so that the same sign of charge goes to one side and the opposite sign of charge goes to the other side. Okay. We've got the same direction of the friction force acting in, like, the wheels are spinning opposite to each other, but that means that they pass the brushes in the same direction on both sides. So that's why it's built that way, I think. Yeah, I'm not actually sure. So that's a way, kind of an oldie worldy way to separate charges using like literally friction, like rubbing a balloon on your hair. But there's way more modern implementations of this and way more way more applications than just electrocuting a bunch of monks or whatever they're doing in that video that I still recommend that you watch. Okay. So what we do now, like we often talk about these parallel plates with charges on them. So that is a common form of capacitor, parallel plate capacitor. So instead of having this jar with this, they were kind of parallel plates, but they were formed into a tube. Now we have different configurations. Okay? They often have a material in between them to increase the capacitance, but we'll talk about that later. Okay. So a capacitor is the combination of any two objects that hold equal and opposite charges, any two conductors that hold equal and opposite charges. Okay, so we've talked about parallel plates, we had these Leyden jars, but basically, if you've got two charges, opposite charges, minus Q and plus Q, they must have a potential difference between them because there's an electric field between them. Right, so E dot DL or DS, I mean, E dot DS gives you a potential difference across from one to another, okay, along the direction of the electric field. So the amount of charge and the potential difference between these two objects, whatever they are, defines the capacitor, okay? It's basically what voltage you need to hold what amount of charge there. For the parallel plate capacitor, we derived this using Gauss's law, maybe last year or the day before. We used Gauss's law and our little pill box. You remember using our little pillbox shape where we did this? And we figured out the flux through one side, the flux through the other side. And for two parallel, like for two plates of opposite charge, the electric field between the plates is sigma, the charge density on the plates, divided by epsilon naught. Okay? And sigma is equal to the total density divided by the area of the plates. So we get this. Okay? The voltage between the plates is the electric field times the distance, because between large parallel plates, the electric field is a constant, like it's straight lines. And we take a straight line distance across. The potential difference is just calculated by the multiplication of these two quantities, and we talked about this last day. So the potential difference is given by this here, QD over epsilon naught A. Okay. Okay, so it's basically E, as we have up here, divided by D, or times by D. Okay, the definition of capacitance is Q divided by delta V. That's the definition of the amount of charge you can hold on these plates given the potential difference you've got across them. Okay, so it's about the potential, the ability to hold these charges here. When you substitute in the delta V, we find an equation for potential difference, or sorry, for capacitance that's equal to epsilon naught A over D. So this is for a parallel plate capacitor. But it's really interesting because capacitance, which is this, Q over delta V, can be written in a way that has nothing to do with Q and delta V. It's just properties of the objects, like of the device. So the capacitance of a device is related to, geometrical properties of the device. It also tells us, how much charge it can hold given a specific, voltage difference across it. But it's defined for devices largely based on their properties. So when you like are building a circuit and you pull out a capacitor, those capacitances are, specific to those specific capacitors, whatever makes them up, like how their geometry, the material inside them, that sort of thing. Okay. So we've got this interesting thing that we've got capacitance is a property of a device, of the geometric properties of the device, but it's also related to what it can do. So the Q and the delta V are related to what it does, and this epsilon naught A over D is related to what it is. Okay, and they're equal to each other. Okay. One thing you can see. Oh, sorry. Go ahead.
I have a quick question, but I think after you're done, I will. Sorry.
No, go ahead. Go ahead.
Okay. I wasn't sure. Like, do charges flow in the capacitor until the potential across the two plates equals the potential of the battery, or charges flow until the potential across the plates until the potential of the battery equals 0?
We assume that the battery has enough power to maintain the same potential difference. So that means that the charges will flow to the plates until the potential difference is equal to the potential difference of the battery. At that point, you have enough sort of reaction forces pushing back against charges flowing this way so that no more charges will flow to the plate. Over time, the plates start sort of rejecting charge flow to them. And when the potential difference between the plate is equal to the potential difference of the battery, then no more charge can flow there. The plates say, we've got enough, that's it. Does that make sense?
Yeah, thank you.
So
Yeah,
the
welcome.
capacity of the plates is limited by the capacity of the battery?
No, not quite. Not quite. The amount of charge on the plates is defined by the potential difference of the battery. And I was just going to get into that here. So I'll tell you something and let me know if you have more questions after. But the capacitance, because it's related, you can write it as a a function of just properties of the device. The capacitance is always the same for that device. Okay. So if delta V goes down, then Q has to go down so that C can stay the same. The capacitance is the thing that stays the same. And the Q and the delta V will adjust each other so that the C remains the same. So if the battery starts dying, and has less ability to provide that delta V, then the amount of charge that can be held on those plates goes down too. Does that make sense?
Yes, thank you.
Yeah, you're welcome. So it's this interesting thing that we can write C as a function of the device, and the device doesn't change. But Q and V can change, so they have to change in the same way. If delta V goes up, Q goes up. If delta V goes down, Q goes down, in order to keep that capacitance constant. Because the capacitance is based on how the capacitor is made. Okay? So that's basically what this slide says. The capacitance is based on geometrical properties. So you have two ways to write this. This is for the parallel plate capacitor only, but it represents how we think about this. C is proportional to the surface area. So if the area of the plates gets larger, the capacitance goes up. You have the capacity to hold more charge. If the distance between the plates goes up, then C goes down. If D gets larger, then the fraction on the right gets smaller, so C has to go down. So the further apart the plates are, the less charge you can hold, the less the capacitance is, and the less charge you can hold on the plates. Okay. C is also always a positive number. If you happen to calculate your delta V as a negative, you just take the absolute value to get the capacitance. Okay. Because we're just talking about the ability to hold charge. We don't care really which plate has which sign of charge. Okay, so if the size of the capacitor goes up, the capacitance goes up. If the distance between the plates goes up, the capacitance goes down. If the plates are moved closer together, if D gets smaller, then that right-hand fraction becomes larger and C gets larger. So if the plates get closer together, if we can move them closer together, C goes up. Okay, but because C is also related to how the circuit works, how you move charges around, what it does, we have this relationship between Q and V that defines how they change relative to each other, because C has to be held constant for a device. That's this, it has the same properties all the time. Okay. You can put an insulating material in between the plates, and we'll talk about why that works next day, I think. But for a capacitor, it's made, it's manufactured, and its capacitance is fixed. Q and V can change in the circuit, but the capacitance is fixed because of the properties of the device. That's the important. Okay, has anyone got any questions there? Okay, the units of capacitance is named after Michael Faraday, famous engineer. And we have been using, for example, we've been using this epsilon naught variable, which is the permittivity of free space. You don't need to know exactly what that means, but we have been using the units of coulombs squared per Newton meter squared for that variable, or that constant. It's also equivalently farads per meter, because 1 farad is coulomb squared per joules, or coulombs per volt. Okay, so that's kind of useful. Okay, now we'll have a parallel plate capacitor. We'll do an example here. Parallel plate capacitor, we're given the area of the plates. I think I most this on top of it. The area of the plates is 1 meter squared. They're separated by 1 millimeter of air. If you're thinking about capacitors in a circuit, you'll realize that this is a huge, a huge thing. It's 1 square meter, a device. So the plates are huge. And they're separated by quite a large distance compared to what you put into like the capacitors you put into a circuit. But we want to find what is the capacitance of this device, and then figure out the greatest amount of charge we can hold on this capacitor if we're right at the maximum voltage or electric field that the device can handle. Okay, so we have a device, we're given the physical parameters, we can figure out the capacitance, and then we're told we have a maximum electric field that air can handle, which basically gives us a maximum potential difference between the plates. So we want to figure out how much charge we can put on those plates before the air breaks down and shorts out. It creates a conducting path between the two plates. Okay, so we'll do that.
So is it because air does that we want to have an insulator to kind of make it not closed?
Yeah, you can put an insulator in there. What we're talking about, it can happen to any device, kind of regardless of how it's made. As long as you can put a high enough voltage, it will break down any material. Like if you can get a high enough electric field that can essentially separate electrons from their atoms in whatever material, air or whatever is between the device, plexiglass, whatever, it can break it down if the electric field or the voltage is high enough. I mean, you can always, like when you're designing some kind of system, you would always put, a margin of safety and make sure that your electric field and voltages never get that high.
Right.
Yeah.
Okay.
Yeah.
Thank you.
Yeah, you're welcome. Separation between the plates is 1 millimeter. So C is equal to epsilon naught A over D for the parallel plate capacitor. So we've got 8.85 times 10 to the minus 12. We'll use farads per meter this time. 1 meter squared divided by 1 millimeter. So we get capacitance is equal to 8.85 times 10 to the minus 9 farads, or 8.85 nanofarads. Okay. Very straightforward. So that's the capacitance of that device. Now we're going to crank up the voltage and see what happens. See how much charge we can put on there before the air between the plates breaks down. Okay, I'm going to go to the next page. Does anybody still need me to stay here? No? Okay. So we're given maximum electric field, let's call it E max, is equal to 3 megavolts per meter. That's pretty big. We know that C is equal to Q over delta V. So what we want to find is Q max. We're asked what's the maximum charge we can hold in these plates just at the instant that the air would break down. So it equals the capacitance times delta V max. Okay. So to find the maximum charge, we need to know the maximum voltage, and remember that C is the same because it's defined by the properties of the device, the area and the distance. It doesn't change. So C is the same. So Q and V are what we vary up and down to get what we want. Okay. Delta V max is equal to the distance between the plates times E max. Okay, we've got our plates. We've got our plates. We've got an electric field E. We've got high voltage, low voltage. So there's a delta V across here, right? And then the distance between the plates gives us this delta V. Is everyone okay with that? Delta V is equal to minus E dot ds, remember? we multiply E and D together in the space between the capacitors. Okay, so this is a variable D. It's not the derivative D, it's a variable, the distance between the plates. Okay. I'm going to go to the next page. Let me know.
Where would we get ds in that problem?
Oh, here, this is the general formula that's on your formula sheet for the potential difference given an electric field. And ds is the little elemental length that you move a charge through the electric field, you know, to do electric work and to calculate the potential energy and potential. Okay, so this is this is a small, like, elemental distance. Okay. This question is a bit extra confusing because we use the variable D here. I should change that. Okay. Let me write it. Let me write it over here. So you don't think it's DE, because that's not what we're doing. It's E times D. Okay. I'm going to go to the next page. Well, this is what we had before. So C times the maximum electric field, which we're given, 3 megavolts per meter, times the distance. That's the meters that cancels out with the per meters in the electric field. So that's the distance between the plates. Okay. So we have 8.85 times 10 to the minus 9 farads. That's the capacitance that we calculated in part A. And then the breakdown electric field, the electric field between the plates that would cause the air to break down and create like a short, a lightning spark kind of. 3.0 times 10 to the 6 volts per meter. And then 1 times 10 to the minus 3 meters, 1 millimeter separation between the plate. So Q max is equal to 2.66 times 10 to the minus 5 coulombs, or 26.6 microcoulombs. Okay. So you could put up to 26.6 microcoulombs on those plates, and at that point, there's such a high potential difference or voltage between the plates that you've built up that it would cause the air to basically break down or disintegrate in between and create a little kind of lightning spark between them, shorting them out. It creates, when the air breaks down, it separates electrons from the atoms in the air or the molecules in the air, and it creates a conducting path between the plates that helps short those out to reduce that voltage. Like, it basically creates a path that allows charge to flow between the two plates. Okay, so when you're charging the plates up, you add charge, add charge, add charge, and it gradually builds up the potential difference between the plates, and you get to a point where the air cannot sustain that voltage anymore, and it breaks down, creates a conducting path, and the plates like basically discharge across the air between them, the broken down air between them. Okay, and that's what you saw in that Wimshurst video, those little sparks between the metal spheres in the Wimshurst machine. Between the little spheres in the Wimshurst machine, those little electrical sparks were the air breaking down between those two spheres. So there was enough charge in those Leyden jars that it created a potential difference between those little spherical balls, and then there's a little spark. Okay. So not every capacitor is a parallel plate capacitor. I see a hand up. Yep.
Just a question. In that last equation, you had delta V equals ED, and in the formula sheet it has delta V equals minus ED. Is that for like an electron, or What's the difference between the two
Yeah.
formulas?
The capacitance is always positive, so I've just used absolute values for these. And if everything is positive, it will keep the capacitance positive. Yeah, thank you for that. It's a bit of a lazy. I did that a bit lazily. So capacitance is always positive. So we're just dealing with magnitudes here. We don't really care which direction the voltage points for this calculation. So we just use magnitudes here. Yeah, good question. Very good question.
Okay, so anytime you're dealing with capacitance, you can just assume that delta V and Q is positive.
When you're calculating capacitance, even if you do choose a negative for delta V, you'll have to take the absolute value in the end to get the capacitance. There'll be applications, like we'll talk about capacitors in series and in parallel combinations in circuits, and there you'll have to know which side of the capacitor is positive and negative, like negatively charged, where the plus Q and minus Q is. But when you're calculating things like this, you just want to know magnitudes. The air is going to break down. You don't really need to know which direction the electric field is pointing. The air is just going to break down. So we just use absolute values here. But yes, V and E are related with a minus sign when you're keeping track of the direction of the electric field and the displacement of the particle. Definitely.
Thank you.
Thanks for noticing that. That's great. Okay, so we'll do a spherical capacitor now. So what we want to know is the capacitance of an isolated sphere, which seems maybe weird and maybe like we wouldn't want to necessarily do that, but it is a thing. We have a charge Q on the sphere, and we have a potential difference between the surface of the sphere and infinity, where V equals 0. We set V equal to 0 there. So you can figure out what the capacitance of this system is. Oops. So we'll do that. So we have our sphere of radius A. Okay. It has some charge Q on it. So outside the sphere, we have the electric field, and we already figured this out using Gauss's law. We have KEQ over R squared, and it's in the radially out direction. This R is the radius to some point P where you want to know what the potential is or the electric field is. So it's the variable. So R is running from infinity right up to the surface at radius A. So R is the variable, okay? Remember, what's the electric field at radius values less than A? Does anyone know? Anybody remember? Electric field inside the sphere.
0.
0.
Hooray! I'm very excited. Okay. And we also did this last day. The potential outside the sphere is this formula where we set V at infinity equal to 0. We set that as our reference point, okay? So when we talk about the potential at position R, it's relative to potential 0 at infinity, okay? There's no absolute potential, remember that. We just happen to set the potential equal to 0 at a convenient. Okay. So at the surface, VA is equal to K Q over A, right? If we come right into just on the, just barely outside the surface so that the charge is enclosed here, the potential is A. And then remember that V of A, this is also V inside the sphere, okay? So we come right up to the surface and we get this potential VA here, and then that's the value everywhere inside the sphere because the electric field inside is 0, so the voltage becomes constant inside, and it's whatever it is at the surface, okay? So we're actually looking for the capacitance. So we're looking for the potential difference, VA minus V infinity. That is equal to the delta V that we want in our capacitor equation. Okay, so we'll get that. I'm going to just create a new page here so we don't get too crowded. Okay. Delta V is equal to VA minus V at infinity. So that we set to 0 when we're doing all this derivation in the first place. So we get KEQ over A. C is equal to Q over delta V. Okay. So we do Q over KEQ over A. So the Q's cancel out, and we get A over KE. Okay. QE is 1 over 4 pi epsilon naught, so you can also write this as 4 pi epsilon naught A if you wanted to. Okay. So this is the version of the capacitance that is just a function of the properties of the device. So we have a radius A of the sphere and nothing else in here, okay? Okay. So the capacitance is related to the size of the sphere. Okay. Good. So we're going to do the same thing, but with a more physical device that you might actually use. Instead of having the capacitance relative to infinity, we're going to have it relative to a sphere that's just a bit bigger with the opposite charge. Okay. Does anyone got an idea how we might do that? Anybody know? We know the potential at each sphere, right? Right? So we can figure out the potential difference between the spheres. And then we're good to go. Okay. So we do the same thing, except instead of coming from infinity, we're coming from the outside sphere. Okay, so this has, which one does this have? R1 here, and then R2 here. The electric field between these two spheres is created by the charge enclosed, so it's related to this sphere inside. And we want to calculate the potential difference. So here is where we need, to do our little integral. Okay, so this is the electric field between R1 and R2. Okay, because we're following this electric field along some path defined by ds in the same direction. Okay, ds is equal to the radial distance in the radial direction, and E is radial also. Okay, so E dot ds is equal to E times ds. Okay, because they're parallel in the same direction. We know that the electric field due to a spherical charge outside the spherical charge is KQ over R squared. Okay, that's generally true for a spherical charge Q. Okay, and for our case, R1 is less than R2. So we're looking in the region between the two spheres. Okay, so we're going to find delta V between the inside sphere and the outside sphere. That defines the capacitance of those two spheres. Okay, so delta V is equal to the minus the integral R1 to R2. So here's our electric field, KEQ over R squared, times ds, which in our case is dr. And when you do the dot product, you end up with just a number, right? Just a number. There's no vectors anymore. So we integrate dr over R squared from R1 to R2. That becomes our integral. The integral of dr over R squared is minus 1 over R, and then we have to put our limits on it from R1 to R2. Okay, everyone following along here? So we've got KE, which is a constant, Q is a constant, and we've done our integration 1 over R. We had a minus sign out in front of the integral, and then when we do the integral, we get another minus sign, so they cancel out. So we integrate from R1 to R2. So delta V is equal to KEQ times 1 over R2 minus 1 over R1. Okay. This turns out to be negative just because of the direction that I did the voltage potential difference. The potential at the outer sphere is lower than the potential at the inner sphere, which is smaller. And I calculated it from the inner to the outer, so the potential difference will drop, or the potential will drop going from inside to outside. But it doesn't matter which direction we pick because the capacitance is always the absolute value. Okay. So it's equal to Q over KEQ 1 over R2 minus 1 over R1. The Q's cancel out, we need absolute values there. So I'm just going to go up here and do a bit of rearranging. C is equal to R1, R2 over KE R2 minus R1. Absolute value. Okay, you don't have to do that, but you can do that. Okay. Anybody got any questions there?
That uppercase Q is the source charge in the middle?
Yes. I'm going to flip back to the diagram here. So this chart, the inner sphere has charge plus Q and the outer sphere has charge minus Q. So we find the potential difference by integrating the electric field between the two spheres. But because the electric field is only, like between the spheres is only due to the charge enclosed, only the inside charge contributes to the electric field in this region. Right? Does that make sense?
Thank you.
Yeah, you're welcome. Okay. So there's our answer. I won't do this example. I just want to show this to you. There are other configurations like a cylindrical capacitor. That's like a coaxial cable. It's very common in communication systems, and you can figure it out doing the same thing. You did a question, your question 7 on assignment 1 was a cylindrical like tube of charge, a surface charge. That is exactly what you need to calculate the capacitance of a device like this. in your question, you calculated the electric field due to like a cylinder of surface charge or a tube of surface charge, which is what you have when you have a conductor with some width with a charge on it, because all the charge goes to the surface. So you basically calculated this already in assignment number. Okay. Here, the answer is here, but so in general, capacitance is an absolute value. It's defined by the device, the geometry of the device, the physical properties of the device. It's also defined by the material between the conductors, but we haven't talked about that. Even though the capacitance is defined in two ways. It's defined by the properties of the device, which set the capacitance C equal to a constant. It's also defined by the charge and the voltage, which is what the capacitance does. So it's defined by what it is, which is the properties of the device, and what it does, which is separating charges with a potential difference. Okay? Because the device has the same capacitance all the time, if you change the charge that the plates or the device holds, then you have to change the voltage so that you can keep that C value constant. Okay? Okay? Are we good with that? I have posted already, we didn't get as far as I'd hoped today. I've posted capacitors in parallel and in series, so I'd like you to take a look at that before next day. So we'll be talking about capacitors in circuits and energy stored in capacitors next day. Okay, so take a look before we get there. It's in the textbook, but I think this is a little bit more detail. Does anyone have any questions related to this or anything else? Anybody? If you have trouble accessing assignment 2 from Canvas, let me know. For some reason, the link, the WebAssign link keeps disabling itself. It's very weird. So if you can't see it, if you can't see the link to assignment number 2, you can go directly to WebAssign to get it, but let me know and I'll fix it up for everybody. The integration is a bit weird between WebAssign and Canvas. Okay. There's nothing else. I will shut this down, but I'm happy to stick around and answer questions if anybody's got any.
I got a weird question for you. So you were talking about the electric potential differences or whatever, and there's like breakdown. So I was thinking about like Tesla towers. Is that how that works?
Yeah, probably. As a teaser, where's my working lecture 7? Not done the setup for this one yet, but
That's fine. I was just thinking about it. I was wondering how he thought through the process himself. And
yeah. I'm gonna share my screen again for a second here because it's very cool. You can get a preview next day if you want. This maybe, I don't know, I'm not sure if this is what you're talking about, but
yes, I saw a little sneak peek. That's pretty much what I'm talking about.
Yeah.
And then like the next application would be like radio waves and stuff, but that's kind of, I don't know if that functions the same. I was just thinking about communication and electrons. It's kind of neat how I can sort of do that now.
Yeah, communication and radio waves. So here's the electrical breakdown. So that's the conducting path that's shorting out those two poles there.
Yeah.
It's kind of amazing, actually. So,
I wonder why it's rising.
because the air is breaking down and it's heating up. And
so the hot air rises.
Yeah,
kind of
exactly.
Thing.
Yeah. So it's the conducting path is getting lifted a bit. Anyway, the communications part is related to the waves module that you'll do at the end.
Oh, okay.
It doesn't break down the air like this, but oscillating electric and magnetic fields are called electromagnetic waves. Those are radio waves.
Yeah.
And those can travel and carry information with them. Yeah.
Alrighty, thanks for the insight.
Yeah, no problem.
Could you replay that video one more time?
Sure. Oh, sorry.
Okay, so does that so the wires that they're on, they know that they overheat or that they that overcharge, so they move to separate by themselves?
Oh, I don't
Or
know.
was it burning them? Because
Uh,
right when the spark happens, I just saw
oh
them
yeah, it burned it.
pulled.
Yeah,
Oh, okay.
yeah. I don't know what was between it. It was probably an insulator between it, and it just broke it down. Like it just broke.
Okay. I wasn't
Yeah.
sure if it was like designed to just separate and stop. but-
Yeah. So this, like, if you put plexiglass and basically connect it to too high voltage, it will break down the material like this. So, yeah. Indeed.